Welcome to a walkthrough or an exploration of JMESPath. JMESPath tutorial. This is a tutorial of the JMESPath language. JMESPath is a query language for JSON. You can extract and transform elements from a JSON document. The examples below are interactive. You can change the JMESPath expressions and see the results update automatically. For each of these examples, the JMESPath expression is applied to the input JSON on the left, and the result of the evaluating JMESPath expression is shown in the JSON document on the right-hand side. Basic expressions. The simplest JMESPath expression is an identifier, which selects a key in a JSON object. So to play around with this, if I change that to C, B, it automatically changes. Try changing the expression above to B, C, and note the updated result. Also note that if you refer to a key that does not exist, a value of null is returned. For instance, D. You can use a sub-expression to return nested values in a JSON object. So working my way just right backwards. Oops. Let's back up the tree, whereas if I do, there is no C property underneath the A key, so it returns a null. If you refer to a key that does not exist, a value of of null is returned. Attempting to subsequently access identifiers will continue to return a value of null. Try changing the expression to B.C. Index expressions allow you to select a specific element in a list. It should look similar to array access in common programming languages. Indexing is zero-based. Oh, -1 does work. I wonder if it understands the spread operator. It does not. Oh, that's... Doesn't seem to be a way to get multiple. If you specify an index that's larger than the list, a value of null is returned. You can also use negative indexing to index from the end of the list. -1 refers to the last element, -2 refers to the penultimate element. Try it above. You can combine identifiers, sub-expressions, and index expressions to access JSON elements. So A dot B dot C, the 0th indexed element in that array, and then within that, the D key, the one indexed array. Inside that array, the 0th. My oh my. And then you go into that. Go. Oh. Because the 0th is not an array, it is just go all the way back, show B, very ugly looking JSON layout. Slicing. Slices allow you to select a contiguous subset of an array. If you've ever used slicing in Python, then you already know how to use JMESPath slices. In its simplest form, you can specify the starting index and the ending index. The ending index is the first index which you do not want to include in the array. Let's take a look at some examples. First, given an array of integers from 0 to 9, let's select the first half of the array. This slice contains the elements 0, 1, 2, 3, and 4. The element at index 5 is not included. If we want to select the second half of the array, we can use this expression. The two examples above can be shortened. If the start or step value is omitted, it is assumed to be the start or the end of the array. For example, that's how you use steps. Try changing the example above to only include the last half of the array elements without specifying the end value of 10. The general form of a slice is start, stop, step. So far, we've looked at the start, stop form. By default, the step value is 1, which means to include every element in the range specified by the start and stop value. However, we can use the step value to skip over elements. For example, to select only the even elements from the array. Also note, in this example, we're omitting the start as well as the stop value, which means to use 0 for the start value and 10 for the stop value. In this example, the expression is equivalent to. The last thing to know about slices is that just like indexing a single value, all the values can be negative. If the step value is negative, then the slice is created in reverse order. So if I wanted to start from the negative first and grab down to the negative fourth, so then we'll grab negative 1, negative 2, negative 3. And because of the negative there, puts it in reverse order. That does not work because it wants to have them go in that order. Okay. The above expression creates a slice, but in reverse order. If you want all the details about how slices work, check out the section in the JMESPath specification. Projections. Projections are one of the key features of JMESPath. It allows you to apply an expression to a collection of elements. There are 5 kinds of projections: list, slice, object, flatten, and filter. List and slice projections. A wildcard expression creates a list projection, which is a projection over a JSON array. This is best illustrated with an example. Let's say we have a JSON document describing a people, and each array element is a JSON object that has a first, last, and age key. Suppose we wanted a list of all the first names in our list. So within people, star.first. So the star almost looks like it grabs everything, every element in the people array, and then is it only returning the first key. In the example above, the first expression, which is just an identifier, is applied to each element in the people array. The results are collected into a JSON array and returned as the result of the expression. The expression can be more complex than a basic identifier. For example, the expression foo star dot bar dot baz 0 would project the bar dot baz 0 expression to each element in the foo array. There's a few things to keep in mind when working with projections. These are discussed in more detail in the wildcard expression section of the spec. But the main points are: projections are evaluated as 2 steps. The left-hand side creates a JSON array of initial values. The right-hand side of a projection is the expression to project for each element in the JSON array created by the left-hand side. Each projection type has slightly different semantics when evaluating either the left-hand or right-hand side. If the result of the expression projected onto an individual array element is null, then that value is omitted from the collected set of results. You can stop a projection with a pipe expression discussed later. A list projection is only valid for a JSON array. If the value is not a list, then the result of the expression is null. You can try this out in the demo above. Notice how people star.first only included 3 elements, even though the people array has 4 elements. This is because the last element, missing : different, evals to null when the expression first is applied. The null values are not added to the collected result array. If you try the expression foo star dot bar, you'll see a result of null, because the value associated with the foo key is a JSON object, not an array, and a list projection is only defined on JSON arrays. Slice projections are almost identical to a list projection, with the exception that the left-hand side is the result of evaluating the slice, which may not include all the elements in the original list. So the example above checks inside the people array, goes from beginning, stops at the 2 indexed item, so it will only grab the indexes 0 and 1, and then their dot first property. As you can see, James Jacob, but not Jaden. Object projections. Whereas a list projection is defined for a JSON array, an object projection is defined for a JSON object. You can create an object projection using the star syntax. This will create a list of the values of the JSON object and project the right-hand side of the projection onto the list of values. oops.star.numargs looks inside the oops key for all properties and then returns any of those that have a numargs key. In the example shown, function A and function B both have numargs. Function C, though, has a veridic. In the example above, the star creates a JSON array of the values associated with the ops JSON object. The right-hand side of the projection numargs is then applied to the JSON array, resulting in the final array of 2, 3. Below is a sample walkthrough of how an implementation could potentially implement evaluating an object projection. First, the object projection can be broken down into 2 components, the left-hand side and its right-hand side. The left-hand side is ops, the right-hand side is numargs. First, the left-hand side is evaluated to create the initial array to be projected, evaluate ops, and input data into an array of the 3 properties from those keys. Then the right-hand side is applied to each element of the array. Evaluate numargs from that JSON object, and only the first and second have it, or the third is erratic. Any null values are not included in the final result, so the result of the entire expression is therefore 2, 3. Flatten projections. More than one projection can be used in a JMESPath expression. In the case of a list object projection, the structure of the original document is preserved when creating projection within a projection. For example, let's take the expression reservations star.instances star.state. This expression is saying that the top-level key reservations has an array as a value. For each of those array elements, project the instances star.state expression. Within each list element, there's an instances key, which itself is a value, and we create a sub-projection for each list element in the list. Here's an example of that. So under the reservations, there's 2 JSON objects, each with the key instances. Within each of those instances, the top one has 2 different states, running, stopped. The bottom one has 2 different states, terminated or running. And so the flattened output from this projection has now an array of arrays that show the running stopped in the first array, terminated running in the second array. The result of this expression is as seen, which is a list of lists. The outer list is from the projection of reservations, and the inner list is a projection of state created from instances star. What if we just want a list of all the states of our instances? We'd ideally like a result running, stopped, terminated, running. But in this situation, we don't care which reservation the instances belonged to. We just want a list of states. This is the problem that a flattened projection solves. To get the desired result, you can use the empty brackets instead of the star brackets to flatten a list. Reservations, empty bracket, dot instances, empty bracket, dot state. Try changing star to empty brackets in the expression above and see how the result changes. While the spec goes into more detail, a simple rule of thumb to use for the flatten operator, empty brackets, is that it flattens sublists into the parent list, not recursively, just one level. It creates a projection. So anything on the right-hand side of the flattened projection is projected onto the newly created flattened list. Interesting. So even just removing the second star instead of the first star had a similar effect. You can also just use empty brackets on its own to flatten a list. And then do another one to go another layer deep. If you flatten the result expression again to empty brackets, you then get a result 0 through 7. Try it out in the example above. Filter projections. Up to this point, we've looked at list slice projections, object projections, and flatten projections. Evaluating the right-hand side of a projection is a basic type of filter. If the result of the expression evaluated against an individual element results in null, then the element is excluded from the final result. A filter projection allows you to filter the left-hand side of the projection before evaluating the right-hand side of a projection. Let's say, for example, we have a list of machines. Each has a name and a state. We'd like the name of all machines that are running. In pseudocode, this would be start an empty array called result for each machine in input data with the key machines. If machine state equals running, result dot insert at end machine name return result. A filter projection can be used to accomplish this. A filter projection can be used to accomplish this. Machines brackets question mark state double equals running dot name. In the input data, there are 3 machine objects listed with names A, B, and B. Machine A has a state of running. Machine B has a state stopped, but then also a line where the state is running. So the result shows AB. Try changing running to stopped in the example above. You can also remove the .name at the end of the expression if you just want the entire JSON object of each machine that has the specified state. A filter expression is defined for an array and has the general form left-hand side, bracket question mark expression, comparator, expression, end bracket, right-hand side. The filter expression spec details exactly what comparators are available and how they work, but the standard comparators are supported, i.e. double equals, not equals, less than or equal, greater than or equal. So the dot name could be removed, and so it returns the entire JSON object. Bring the name back in. Change running to stopped and only B. Change that to C. I feel as if that might have been an error to have 2 different B's. Pipe expressions. Projections are an important concept in JMESPath. However, there are times when projection semantics are not what you want. A common scenario is when you want to operate of the result of a projection rather than projecting an expression onto each element in the array. For example, the expression people star dot first will give you an array containing the first names of everyone in the people array. What if you wanted the first element in that list? If you tried people star dot first bracket 0, that you just evaluate first bracket 0 for each element in the people array, and because indexing is not defined for strings, the final result would be an empty array. To accomplish the desired result, you can use a pipe expression, which has expression, pipe, expression, to indicate that a projection must stop. This is shown in the example below. So if we run the JMESPath query, people star bracket dot first, pipe that into a 0 bracket, it returns James, because the projection first, the projection on the left-hand side of the pipe would find any JSON objects in the people array that have a property dot first, which it would find 3, and it would return the value of the first key, which are James, Jacob, Jaden, return that as an output array. That output array is then piped into the next JMESPath query, which asks for the 0th index of the array, which would be James. In the example above, the right-hand side of the list projection is first. When a pipe is encountered, the result up to that point is passed to the right-hand side of the pipe expression. The pipe expression is evaluated as seen below. Multi-select. Up to this point, we've looked at JMESPath expressions that help to pare down a JSON document into just the elements you are interested in. This next concept, multi-select lists and multi-select hashes, allow you to create JSON elements. This allows you to create elements that don't exist in a JSON document. A multi-select list creates a list, and a multi-select hash creates a JSON object. This is an example of a multi-select list. People, empty bracket, dot, bracket name, comma, state dot name. The provided example data, there are 3 JSON objects within the people array. Name A with state name equal to up. People name B with state name equal to down. People name C with state equal to name up. So running the people open bracket dot name comma state dot name creates an array of arrays that has the state name for each people name. So the first array in our output is A comma up. The second array is B comma down. The third array is C comma up. In the expression above, the name comma state dot name portion is a multi-select list. It says to create a list of 2 elements. The first element is the result of evaluating the name expression against the list element, and the second element is the result of evaluating state dot name. Each list element will therefore create a 2-element list, and the final result of the entire expression is a list of 2-element lists. Unlike a projection, the result of the expression is always included, even if the result is a null. If you change the above expression to people empty bracket dot foo comma bar, each 2-element list will be null comma null. A multi-select has the same basic idea of a multi-select list, except it instead creates a hash instead of an array. Using the same example above, if we instead wanted to create a 2-element hash that had 2 keys, name and state, we could use this. Before diving into that, I just want to refresh people empty bracket, flattens it down, so now people empty bracket returns the entire I'm going to go remind myself real quick how the flatten works. Okay. Now back to a multi-select hash. People, empty brackets, dot, curly braces, name, the new property name will equal old property name. New property state will equal old property state dot name. So the result is a list, an array, of 3 JSON objects that show the name and state.name of each of the original lists, or the original JSON objects in the original list. Function. JMESPath supports function expressions. For example, length of people would return 3 in the below sample data because people has a key value of a 3-element array. Functions can be used to transform and filter data in powerful ways. The full list of functions can be found here, and the function expression spec has the complete details. Below are a few examples of functions. This example prints the name of the oldest person in the people array. Max by people, comma, and age dot name. So it seems to look in the people's key for anything, any objects within that array that have an age property, finds that name A, that people A, person A, has the highest age of 50, so it returns A. Functions can also be combined with filter expressions. In the example below, the JMESPath expressions finds all elements in myArray that contains the string foo. MyArray, question mark, contains at, really at refers to this object, comma, foo equals true. Within the myArray key value array, there's foo, foobar, barfoo, bar, baz, barbaz, barfoobaz. So there should be 1, 2, 3, 4 elements in the output array, and there are. The at character in the example above refers to the current element being evaluated in myArray. Okay, so it doesn't reference back to the myArray list. The current element being looked at. So it's almost like a for each item. The expression contains at foo will return true if the current element in the myArray array contains the string foo. While the function expression spec has all the details, there are a few things to keep in mind when working with functions. Function arguments have types. If an argument for a function has the wrong type, an invalid type error will occur. There are functions that can do type conversions, to string to number, to help get arguments converted to their proper type. If a function is called with the wrong number of arguments, an invalid arity will occur. Next steps. We've now seen an overview of the JMESPath language. The next things to do are see the JMESPath examples. You'll see common JMESPath expressions that go beyond the tutorial. You'll also see how to combine multiple features together in order to best leverage JMESPath expressions. To actually start using JMESPath, pick the language of your choice and check out the JMESPath libraries page for more information on using JMESPath in the language of your choice. Read the JMESPath spec, which has the official A, B, and F grammar and full details of the semantics of the language.